Okay, so this is just a sort of a little extra video I put together where I basically just used EES to calculate the all the relevant parameters of the Carnot cycle. Um, all the relevant parameters of the Carnot cycle in using water as the working fluid. Um, all right, so basically I use these to calculate all the properties. I'm operating between uh, 473 Kelvin and 353 Kelvin, whatever that comes out to be in Celsius. And I calculated all of the relevant properties, and using the same processes. So you have to fix the state at one of the properties, right? You have to fix it completely. Otherwise, if you're looking at the plot itself, you have to fix the value at one of these points. Otherwise, this whole process or this whole cycle could move around inside here, right? So you fix it at one, and then you use the process to guide it to the subsequent points. So as plotted on a say a PV diagram, which is something we're a little bit more familiar with, I fixed the state at point 1 because I said the quality was at 0. So it's a saturated liquid at the high temperature. Okay. And then I proceed at constant temperature, which, because it's in the dome, also happens to be constant pressure because it's under the dome. Constant pressure and temperature and I fix the state at state 2, where I'm saturated vapor now, also at the high temperature. Then from there to here, it's adiabatic, right? So there's no heat transfer, i.e., the entropy, like we just discussed, the entropy remained constant. Okay, so entropy is related to heat, right? It's the heat divided by the temperature. And so because it's adiabatic and there's no heat transfer and there's no, it's reversible, so there's no entropy generation, the entropy at state 3 and state 2 is going to be equal to one another. So this line here represents roughly which one was it? 2 and 3. So this line right here is a line of constant entropy. So in reality, we go from point 2 down this dashed line to point 3. And then from point 3, from state 3, I guess, we proceed at constant temperature. And because it's under the dome, we're also at constant pressure over to state 4, and then the cycle repeats. So from state 4 to state 1, we again proceed up in adiabatic line. It's just a little, a little bit of rounding error there, so it doesn't look like it's quite on the line, but it is. The idea is that it's on this dashed line, constant entropy line from state 4 back up to state 1, and then the cycle repeats. Okay. Okay, so say I wanted to generate one of these property plots myself. I could hit this property plot. I'm going to choose water as the fluid. In this particular case, I want to do a plot, a diagram of temperature versus entropy. Okay, so these are your options. These are all the various options you have. You could choose which lines of constant pressure or specific volume, and that changes as a function of which two properties you're plotting. But for a TS diagram, you have an options of pressure and specific volume. Then and you can show lines of constant quality there anyway. So hit OK. All right, so now this is just a general plot of the saturation dome and the relevant lines of constant specific volume and pressure and quality of these little gray ones down here. But I can overlay I can overlay our cycle on top of it. And so for the x-axis, in this case, I'm plotting entropy, and I'm plotting temperature versus entropy. So the y is temperature, x is entropy, and I have all these. You notice I have all these values defined now. So these are all quantities that are available in the array table. And so say I want to plot it in red dots. I want it to automatically update. So if I change some of these quantities, I want the plot to move around. And I want to put point levels, and the subscript number is good. To get them to join together, I have to define this state 5 in order, and just basically it just sits right over top of the state 1. There you go. And so this is what it looks in a TS diagram, because you remember it goes for, it's constant pressure, or I'm sorry, constant temperature and constant entropy. So it's just a rectangle. And you know, basically this is identical. Another interesting fact, like I can probe around inside this diagram using this little red crosshair button here, and it gives me all the other state variables associated with every point in this plot. So it's an interesting thing to illustrate what this plot really is. Okay, I just thought it was cool, so I was gonna show you guys that stuff. I guess the point of me doing this actually was to show the I calculated using in 2 different ways. I calculated the thermal efficiency using the traditional way. I calculated the net work for the cycle, and I divided it by the heat input. And then I calculated it also using the formula for the reversible heat engine. Okay, and I just wanted to illustrate that those 2 values came out to in fact be identical. Okay, and so that was a simple way of illustrating it, but that's all I really have to say about that.